And hello YouTube, welcome back. I'm going to continue the discussion of the kOmegaSST model. So in the last video we were talking about this equations, the k plus equation, and there are two expressions, one for the log law and one for the this viscous sublayer. And you might be wondering what this ck is. Of course, from intuition, since it is the viscous sublayer, there should not be any turbulent kinetic energy inside the viscous sublayer, so ck should be 0 just by intuition. Okay, there is no turbulence in the VSL, viscous sublayer, so ck equals to 0. That should be the correct kind of expression. Okay, so how do we get that? There is actually a rigorous proof of that. I'll just quickly go through that. Remember we were here, we were over here. Okay, to derive the above, recall this, and then we said that this left hand side is 0, but for the turbulent sublayer, this production term cannot be 0 now. So we have to kind of factor that in, and this production term, after you non-dimensionalize it, it will be equals to plus nu t plus du plus dy plus. This whole thing should be squared. Now where did this term come from? This is the production term. So if you remember from your k epsilon model, the production term is this. It is the negative of this Reynolds stress term and the velocity gradient of the average velocity. So if you use the so this is the dynamic production rate, because that one's including the density. Okay, so this pk dynamic divided by the density, that will be equals to the Reynolds stress terms. So I do a bar u I uj, and partial u partial y. So remember this, the hypothesis is that this can be written in some turbulent viscosity times du dy. So we non-dimensionalize it to get this form over here. Alright, so, and in the turbulent sublayer, we cannot just assume remember in the viscous sublayer we actually assume this. Where is it? In viscous sublayer we assume this. Alright, in viscous sublayer we assume this, but in turbulent sublayer we assume nu t is much greater than nu, so that I think I need to get this here. So the turbulent sublayer, we have to include the turbulent portion of this viscosity, we cannot just assume it is 0, because now it's the other way around. So we assume the turbulence sublayer nu t is more than nu, much greater, so that this one can kind of disappear. Alright, and then of course we need to put this in. Alright, so that's how we kind of get this equation here. Kind of get this equation here. Of course, I must change let's change this to omega star and C mu over here. Okay, so we assume here this term is small in turbulent sublayer. This term is small, especially compared to this. This one is the Reynolds stress. So the diffusion of turbulent kinetic energy is much smaller than this. So in turbulent sublayer, we can almost approximate this as 0. All right. So doing so, doing so, we can integrate this as such. This whole thing can just become some constant ck. Okay, ck. That's where the ck actually comes from. Then of course the problem is how do you get this ck? All right. So just slow down. I'll slow down a little bit. Remember, we say this term is small and this is equals approximately to 0, and then from that we find that this whole term we can just put it as a constant. Okay, this whole term we can put it as a constant, and what we are left with is this. This will be equals to 0 now, and then we can do the following. Yeah, we can do the following to this equation. So this one is the omega star version, so we can use this equation. Okay, nu t plus equals to omega star plus, was it k or k over omega star. So k plus divided by omega star plus. Okay. Alright, k plus over omega star plus. So yeah, k plus over omega star plus. We use this substitution. Okay, we use this substitution, and we put this back in here. All right, we put it back in here. Okay, omega plus omega star plus equals to k plus divided by omega or nu t. Is it nu t? No. Omega star plus equals k plus over nu t plus. Right, there we go. We just substitute that in as follows, and we get this. So we'll have k plus squared, and if we just multiply everything by nu t, you get the following. There you go. We'll have an equation for k. Alright, we'll have an equation for k. Or the other way around it, if you want to get rid of the k over here, you want to get rid of k here. So we want an expression in omega in terms of this du dy. So that's what we are doing. So omega star plus equals to, or rather I do a k plus. K plus equals to omega star plus times nu t plus. Alright, I substitute this into here and we'll get the following. Alright, so we can kind of get rid of this nu t. Squared here. Alright. Then we have omega star plus equals to, finally, du dy over square root of mu, c mu. So that's how we get that equation on the bottom. Right, so this is how we get this equation. Alright, this is how we get this equation. The question, of course, is what is du dy? Okay, what is du plus dy plus in log law region? That's very simple because we already have more functions for this, and the way to find that is to, okay, that's our more function. Okay, I'm going to find my more functions, and there we go. Where to is this thing? Oh, okay, I think we almost found it. Yeah, this is the wall function. We go to kOmegaSST, and there we go. This is the log law region. Okay, or rather u plus equals to 1 divided by kappa ln y plus 5.5 kappa equals 0.4. Yeah, kappa equals to 0.4, and then if we just take a du dy plus of this, okay, du plus dy plus, that will just be equals to, okay, 1 over kappa. This term disappears. Ln y just becomes reduced to 1 over y plus. Right. There we go. And we substitute this in the omega star plus, and we get an equation for the omega side. So this is roughly how we get our omega. Kappa y plus. So we take a look at this and we compare to this. This is how we derive it. And of course, now we want to get back our k equation. K equation. Alright, so we remember that, remember this. Remember this term. Alright, so we can just copy and paste this down here. Okay, copy and paste this, and then we have okay, we will just have this, and then the question is, what is nu t plus? What is nu t plus? Nu t plus is over here. yeah, the simplest way is to get this equation. If you remember our wall shear stress equation, tau wall, okay, tau wall equals to rho nu plus nu t, okay, u partial y. All right. If you non-dimensionalize, then we get this 1 equals to 1 plus nu t divided by nu. Okay, nu t over nu du plus dy plus. I kind of change the caps every now and then from here to there, depending on what it, yeah, depending. But that's basically what nu t is about. In the log law region, okay, nu t, or rather nu t, yeah, nu t is much greater than nu, so we get the following. This all equals to 1. Okay, so nu t plus equals 1 divided by du dy. Alright, this is very convenient for us. Alright. Okay, substitute this back. And we get this 1 over du dy is here. And what is 1 over du dy? We just have this kappa y plus. Okay, this is just kappa y plus, and therefore we have this. Oopsie, 1 over c mu square root c mu. Okay. Right. Okay, so that is how we get our k plus for the log law region. Okay, k plus for log law region. All right, k plus for the log law region is as follows. That's how we derive it. Yeah, so basically it's just swapping around many times of this equation. So that's the long and short of it. Yeah, so question is for the intermediate region. Okay, we remember we have a log law region of here. This is a, okay, I have 3 regions here. This is the viscous sublayer. This is log law. And then this one is sometimes called the buffer region. Okay, the buffer region is somewhere in between where neither of these laws hold. How do we handle the viscosities over here, or handle the k and omega here? So omega in the viscous layer. So what they do is very simple, or rather omega star in the viscous in the buffer region. It's they calculate it like so in CFD code. Okay, it becomes omega star in the viscous layer plus, so they take a root mean square of both of them. Okay, in the log region, omega star in the log region square. Okay, so they just have a root mean square of both of them, and that's why we have this expression over here. Okay, we have this expression over here. In the intermediate region, omega plus is approximated with some form of interpolation between the viscous sublayer value and the log layer value. So it is suggested, one of the suggested ways is to use this, and this is what you will see in OpenFOAM code or some CFD code. yeah, they have this kind of correlation over here. Okay, so this is how we deal with omega. Okay, between the viscous sublayer and the log-law layer. All right. So in the intermediate region, we take root mean square of viscous sublayer and turbulent sublayer omega. Alright, hopefully this was clear to you. Can be a little bit confusing, but long and short of it, I just showed you how this boundary layer equations actually help us to derive expressions for k plus and omega plus with respect to y. Okay, k plus and omega plus with respect to y. So this is all that you're seeing here. And yeah, we have not derived how we get that ck equals to 0. Okay, where's the ck? Ck should be on top. Here, yeah. You have not derived how ck equals to 0, but just by intuition you can kind of already guess. Okay? And well, I mean, alright, let's do it mathematically then. Okay. How about, okay, let's go back to this question. How about k plus in viscous sublayer? Okay, recall k plus equals to ck into y, y plus to the power of 3.23, and what we have is this equation for k, or for ck rather. That's that equation for ck. I'm gonna scroll up, scroll out. Yeah, ck is here. Alright, it's over here. This is it. Yes. Okay, this is it. So this, in the turbulent sublayer, we have all of this equals to some ck here, and this is where the ck for this is actually from. Okay, so what is this ck? Ck is the value of this at the boundary. So this ck probably comes from one of the boundary conditions. Okay. So okay. So remember viscous. Let's say this is the viscous sublayer and the log-law region. Okay, I'm ignoring the buffer region for now, just for the sake of illustration. So you have a k plus equals to ck y plus to the power 3.23. all right, so where does this ck come from? It comes from the boundary condition here, okay, between the viscous sublayer and the log-law region. That's probably where it comes from. So this whole term here is equals to ck. So this, when you fit in the boundary conditions, you'll get ck here. I'm not going to go through in detail, but we can quickly prove that ck equals to 0. Okay, so because k plus equals to this, so the differential of this equals to 0. Therefore, ck equals to 0, which fits very well with our intuition that there should be no turbulent kinetic energy in the viscous sublayer whatsoever. All right, so at least if we are using this approach to dealing with the wall functions for k plus and omega plus, then we will get that. Okay, so I'm gonna stop here. Hopefully this helps you to see how we get these equations from. But yeah, if you missed out the calculations, just remember, you know, the rough concept about how we get omega plus and k plus for our boundary boundary layers. Yeah, omega plus and k plus for the boundary layers, and therefore we can start looking at this blending function, because now we have this omega here, or rather we have this omega here, we have k here. All of these are in functions of y, and once they are in functions of y, we can start to deal with how f1, or how these values actually change with y plus. So thanks for watching. I'll see you guys again. Bye bye.